Merhabalar, ses geliyor mu?
Evet hocam, görüntünüz de gayet net, ses de iyi.
Ses geliyor. Ben şimdi sayfamda görünüyor.
Evet hocam. Başlayabilirsiniz hocam.
Tamam, eğer izin verirseniz ben İngilizce sunumu yapayım ama soru ve cevapları tekrar Türkçe yapabiliriz. Sorun değil mi? Ben İngilizce yapayım, ondan sonra soru cevapları inşallah Türkçe devam ederiz. Okay, the design of operational quantum radar. Here, it is a general schematic for a quantum radar. In this presentation, we will, quantum radar is a complex system. So for this presentation, we just focus on the transducer section, and moreover, the receiver that we have designed using the CMOS technology for such a quantum radar. As you can know, there are some different methods for generation of the microwave entangled photon. One of them related to the electro-optomechanical system, tripartite system that can be commonly used to to generate the microwave entangled photon. Here, it is the tripartite systems. The tripartite system, the three cavities, three different cavities that coupled to each other with different method to generate the photon, entangled photon. Here, in this system's electro-optomechanical system, we have three different systems, optical cavity coupled to the microresonator, and the microresonator coupled to the microwave cavity. Here the operation starts from the interaction of a high power laser with the OPTC, optical parametric down converter material, to generate the two photon, and we theoretically and practically has been easily shown that the signal entangled with Idler, and we kept Idler in lab and use the signals coupled to the optical cavity, the output of optical cavity coupled to microresonator. You can consider this as a optical force, and here using apply the optical force, microresonator start to resonate. By resonating the microresonator, the capacitance of the microwave cavity changed. So the LC resonator for the micro cavity properties can be changed by manipulation of this capacitance. So the output of the microwave cavity, we theoretically here, actually this is a small part of my PhD thesis, and we theoretically show that the output of this cavity, this mode entangled with the signal and Hitler, and this is the Hamiltonian related to these systems. We need to analyze the systems using the quantum theory. We have to use the related Hamiltonian, and moreover, the important part that create the entanglement between the systems relating, contributed to the interaction Hamiltonian optical cavity to microresonator to microwave cavity, and moreover, indirectly coupling between the optical cavity and micro.
Hocam kusura bakmayın, bölüyoruz. Slide'ınız varsa ekranınızı paylaşabilme şansınız var mı acaba bizimle?
Ne anlamadım?
Slide diyor. Ekran paylaşımı yapar mısınız acaba bizlerle? Biz göremiyoruz slide'ınız varsa eğer.
Ben şimdi slide paylaşımı yaptım sanırım. Ben bir kere de yapayım. Okay, entire screen share. Şimdi
evet,
görünüyor
hocam,
mu?
şu an görüyoruz. Teşekkürler.
Okay, one more time. This is the electro-optomechanical systems that I discussed. The systems contain three different parts: optical cavity, microresonator, and microwave cavity, directly coupling between the optical cavity with microresonator, and moreover, microresonator coupled to the microwave cavity. So using this Hamiltonian, and moreover, finally using the criteria such as the Simon criteria, we theoretically show that the output of the microwave cavity, I mean this mode, which is in microwave, L band here, L band or S band, is entangled with the optical signal. The other systems that we designed here in the in the electro-optomechanical systems, as you may know, the microresonator frequency is around the microhertz. So that means that the phonon or thermal photon generated by this system can easily affect the entanglement. So to fix the issue, we propose another systems, and this system called optoelectronic systems. Here in the optoelectronic system, we remove the mechanical part and replace the mechanical part with the optical systems. Optical systems here, we design the array of the gold nanoparticles and as a detector, and moreover, parallel with we use the varactor diode. Here, the tripartite system contains the optical cavity in the same way, and the resonator, microresonator replaced with the photodetector and varactor diode, and moreover, this considered as a microwave resonator. In the same way, the output of the optical cavity coupled to the photodetector current. By the way, photodetector is biased in the reverse bias. So using the by coupling the mode with the photodetector, current is generated. This current flowing through the varactor diode, a voltage drop across the varactor that is created by changing the voltage. This is the structure of the varactor diode. Here it is a variable capacitor, is a function of the voltage drop across the varactor diode. So by changing the voltage drop, the value of the capacitance is changed. So this is the LC contain the microwave cavity. So the properties of the LC resonator is changed. So that means that by the way, we using the quantum theory in the same way show that the output output of the microwave cavity is entangled with the optical cavity here, and this is the quantum Langevin equation that we use. But here in this presentation, we just focus on the qubit and coupling of the 4 qubit, I mean transmon qubit to generate the entangled photon, and use this in the quantum radar. And here it is a general schematic that we have designed. Recently focused on the generation of the microwave photon using the transmon qubit. And here this schematic contains two sections, different sections. The section that operate in the subcryogenic temperature, 10 millikelvin, using the transmon qubit. That the transmon qubit contains the qubit coupling with transmission line. And in the following, we will discuss about the output of the transmon qubit or coupled qubit, and we theoretically show that the value for this is very low. So we need some amplifier to be operated at subcryogenic temperature of 10 millikelvin. So we have to use some amplifiers. So the best candidate is the Josephson parametric amplifier. We can use HEMT transistor or HEMT amplifier, but HEMT amplifier cannot be used in the subcryogenic temperature. So the only option is the Josephson parametric amplifier, and we design this amplifier to enhance the signal, and then using the transmission line as a readout, the signal coupled to the receiver. Here, this is the schematic, a general schematic for the receiver. We designed this system using the CMOS technology, 45 nanometer CMOS technology as a system on a chip. And the receiver contains this block diagram, LNA. Here it is the input or output of the transmon qubit. The system here illustrated here operate at the cryogenic temperature 4.2 Kelvin. This is the output of the transmon qubit, or actually Josephson parametric amplifier. Here we designed the LNA, and this is RF amplifier, band pass filter, and moreover we designed the mixer to generate the IF signals, and VCO, voltage control oscillator. And in the following we designed IF amplifier to amplify the IF signal, and moreover you can consider the specification characterization of the sub-devices. For example, this is for LNA. The noise figure of the LNA reach around 0.8 dB. LNA gate gain around 36 dB, and moreover the nonlinearity of the LNA is around minus 45 dBm. And calculation for the VCO, voltage control oscillator, it is the frequency versus voltage. It can be reach around 8 gigahertz, and a typical output of the VCO and output of the mixer, and moreover the other parameters related to the IF and output of the systems. And here let's start with the characterization of the transmon qubit. Here we design such a disk systems. Of course, it is a simple schematic for systems. We use for coupled qubit to each other to generate the entangled photons. Here we just showed a simple schematic for the systems. T line coupled to the qubit. For example, here the red line for the qubit signal or number of photons, and the black for the T line, and blue one is the cross correlation between the T line and qubit. And using the entanglement metric criterion, which theoretically show that it can be possible to generate the entangled between the T line and the qubit. And moreover, we analyze the parameters such as S-log projector probability. You know, of course, the other projectors such as Pauli can be calculated, and using this we can calculate the concurrence, or you know, it is a parameter that we can use to analyze the entanglement or quantum correlation. Of course, quantum correlation between the qubit in the systems and the output signal of the qubit. This is just for single qubit. For coupled qubit to each other, the level of the signal is reached around minus 135 dBm. And finally, this is the characterization for the GPA, Josephson parametric amplifier. It is shown that at the tuning frequency around 0, the gain of the GPA is reached around 20 dB. So using this GPA at 10 millikelvin, we can enhance the signal generated by the transmon qubit. So after that, we can transfer this signal to the receiver or transmitter of the quantum radar to enhance the signal or detect the signal. Okay, and here it is a fully integrated system on a chip that we designed using the 45 nanometer CMOS technology as a receiver for a quantum radar. And as you can see, the dimension of chip illustrated, the chip contained the LNA to RF amplifier, and this is the mixer. And moreover, this is the VCO, the zoom out of the VCO illustrated here. As you can see, there is no any inductor in the VCO, so using the inductorless circuits, you know, we can optimize the dimension of the chip. And moreover, for series IF amplifier, again, no any inductor in the RF amplifier. This is the layout of the systems designed in the Cadence. It is please note that it is not a system engineering that in which, you know, we use some blocks side by side, LNA, RF, I don't know, the mixer and local oscillator. This design is transistor-based design. And moreover, please note that this is the design of the layout design in Cadence, and a specification related to this chip illustrated here. We use the 1.2 volt voltage, and power consumption of the chip is around 122 milliwatt. Noise figure of the chip around 0.9 dB, which is suitable for the quantum application, and RF gain is around 85 dB. Dimension of the systems 0.5 times 0.4 millimeter square. Input signal, typically we use the input signal C-band. Bandwidth, please note that this is a very suitable for covering the around 100 coupled qubit to each other. Bandwidth, this bandwidth, and moreover, output signal is around 60 milliwatt peak-to-peak at IF, zero IF frequency. And here I would like shortly talk about the post-processing results of the receiver that we designed for the quantum radar. The LNA that we use, post-processing, you know that we use the layout rather than the schematic, and model the device. The work starts from this signal. It is, for example, considered as a output signal of the GPA that we need to detect or amplify. LNA, and here RF amplifier, and band pass filter. The output of the RF section is this signal. You know, this is 5.2 gigahertz. After this amplification and band pass filter, the level of signal is reached around minus 65 dB. And using mixer and VCO, the signal of the VCO that we generated illustrated here, the output of the mixer illustrated here. This is time version, and this is a spectrum. So using the spectrum, you can easily see that we have a lot of frequency here, 5.2, 10.6, and other frequency, other harmonics. And moreover here, this is the IF frequency that we need to enhance, we need to detect, and we need finally to digitize. You know, after that, some other processing such as FPGA and DSP can be applied to. So using the IF amplifier design, after 2 IF amplifier, as you can see, the level of the signal at IF frequency is reached to the RF, and after 2 RF amplifier and low pass filter, the level of the signal here, this is the RF signal, 5.2 gigahertz, and it is 0 IF that we can detect and digitize the signal. And this is the signal that is considered as a output of the chip that we designed. And in the this is the comparison between the state-of-the-art circuit here. 3 works illustrated here in the same way. I mean, full receiver design using the CMOS technology, and this work illustrated here. You can compare the result with the state-of-the-art here. Just please note that we have no any PDCA for the CMOS technology operating in the subcryogenic temperature, I mean 4.2. So due to that reason, we modeled using the 300 Kelvin, and the qubit platform is transmon and system full receiver, and RF frequency band C-band, bandwidth 3.6 gigahertz, and noise figure 0.9 dB, and the nonlinearity generated by the chip is around minus 65 dBm, which is very suitable for the quantum applications such as quantum radar or quantum computing, no problem. And the technology that we used is 45 nanometer CMOS. Here, the technology can the other technology can be 22 FinFET, 22 nanometer FinFET, the technology, and area that the design chip area is around 0.22 millimeter square, and chip power consumption is 122 milliwatt. Moreover, I would like to talk shortly about my other designs, the design of the device, such as LNA. You know, the LNA is an important part that can be used in quantum applications. You know, the application LNA is work based on the continuous signal. So continuous signal, quantum signal is a continuous. So if we can design an LNA with a very low noise, it can be easily used to different quantum application. Here, I want to list some of my later experience. All of the design is layout-based modeling in ADS software, Advanced Design System software. This is a 3-stage amplifier for the LNA suitable for quantum application. The specification of the design listed here: gain greater than 30 dB, return loss input and output less than minus 12 dB, and noise figure 0.5 dB L-band operation. And the second version of the LNA that we have designed listed here, a specification of the noise figure and gain illustrated here. Again, layout of the this is the 2-stage amplifier, and in this design we use the HEMT transistor. It is not based on the CMOS technology, and it is because the noise can be reached around 0.05 dB in the MOSFET transistors. Using MOSFET technology, we cannot reach such a noise figure. It is due to the HEMT or indium phosphide HEMT transistor properties that we can reach to such a noise figure and gain 40, and again L-band. And other work that we have designed the LNA for quantum application. And actually, this design is used to enhance the non-classicality. We theoretically show that using such a design and using the HEMT technology or transistor nonlinearity, we can enhance the non-classicality of the signal at 4.2 Kelvin. Of course, for this, we need to optimize the noise figure. And here, for this circuit, the noise figure is reached around 0.009 dB baud. As you can see, the gain of the circuit is very low. And my other study related again to the design of the circuit. And in this study, we relate the aim was to find the relationship between the noise figure and entanglement. Of course, it is not entanglement, it is quantum discord or quantum correlation between the signal. And we found that what the noise here is, it can be minimized, the quantum correlation can be enhanced, and this is the result, classical simulation, and this is using the quantum theory. And here, this is the angular frequency, the frequency around 1.39 gigahertz. It is around 8.6 gigahertz angular frequency, and using the GM is the intrinsic transconductance of the HEMT transistor. The noise figure reach around 0.04 dB. Here it is 0.04 dB, and at this point, the quantum correlation between signal can be dramatically increased. And other study again using the HEMT transistor nonlinearity to enhance the quantum discord or quantum correlation. It is internal circuit of the indium phosphide HEMT transistor that we used, and using the quantum theory. And this is the simple LNA. This can be considered as an input matching network, output matching network, and this is the indium phosphide HEMT transistor using the nonlinearity generated by the indium phosphide HEMT transistor, and by minimizing the noise figure, we theoretically show that the quantum correlation between the quantum correlation, or actually non-classically, that output of the circuit can be enhanced. Okay, thanks for your attention. If you have any question, we can discuss about. Sorular alabilirim eğer.
Hocam bir sorumuz var şimdi size.
Tabii ki.
Attention. I wonder about the modeling of the dissipation in transform qubits. So you have a low pass filter and transmission line. In all cases, you have a dissipation. So how do you model the in your Hamiltonian?
Please repeat your question and which slide you want. Which slide you talk about?
In the transform qubit, case, you have a dissipation, right?
In the
transmission line.
Yeah.
So therefore, how do you model the dissipation in your Hamiltonian?
For transmission line, if based on the frequency that the system works, we can select an infinitesimal section of the transmission line at the given frequency and model the transmission line based on the lumped elements. Each part of the transmission line can be considered as a inductor, capacitor, and moreover, the resistor due to the ohmic loss and something like that. But in the design that we use transmission line, in the circuit, we considered all of the noise generated by the transmission line. An ideal version, we can consider the transmission lines as lossless, but in the all modeling, we consider the thermal photon generation and all of the noise, such as, for example, shot noise generated by the lumped element and involved in the systems, and completely consider the noise effect in the systems.
In the superconducting computers, how many transform qubits have been used now?
How many what?
How many transform qubits have been realized in superconducting computers?
It depends on the performance of both. There is the trend of technology is now based on the 100 coupled qubit or transmon to both, and I heard about 75 coupled qubit or 50 coupled qubit, and IQM works on the 50 coupled transmon qubit to generate to the quantum computer. But it depends on the performance that they need. But it is a very critical using some qubits, coupled qubits to to generate the quantum computer due to some problems such as the bandwidth that can generate each qubit. Each qubit needs around, for example, 10 megahertz to couple. So there are problems in the bandwidths that the analog electron cannot support such a wide band for the quantum computer. So there are some critical points. But the trend is, I think, 75 qubits or 100 and something like that.
One more question about the entangled transform qubit realization. Have you realized entangled transform qubit?
I didn't get your question well. Would you please repeat?
I wonder about the entangled transform qubits.
Mhm.
Did you realize it?
Yes, of course, the entanglement that the qubit, the qubit, transmon qubit operate in the subcryogenic temperature, 10 millikelvin. So the coupled, for example, we theoretically modeled the 4 coupled qubit. It is my work, my own work. We theoretically designed these systems and generate the entangled photons. It is entangled, but after the qubit, we need to couple the qubit output to GPA. After the GPA, the entanglement cannot be considered. It is the quantum correlation or quantum discord that we can consider after the GPA. Both using the 4 coupled qubits or 10 coupled or others, it is possible to generate the entangled photons, for example, in C band or X band and something like that.
Teşekkürler.
Teşekkür
Sayın
ederim hocam.
Doktor Ahmet Bey konuşması için teşekkür ediyoruz. Sağ olun hocam. Teşekkürler.
Rica ediyorum. Sağ olun, siz de sağ olun.